For this problem, we're given water in a manufacturing plant is held in a large cylindrical tank of diameter 20 metres. Water flows out of the bottom of the tank through a tap at a rate proportional to the cube root of the volume. For part A, we want to show that t minutes after the tap is opened, that dH by dt is equal to minus k, the cube root of h, for some constant k. And they give a small diagram for this question of the cylinder with the water at a height h and then a diameter there of 20 metres. So we've got quite a bit of work to do for part A, and once we've generated that, we're going to use this solution for part B, where we're going to look at the differential equation. So let's have a look at what information we've been given then. So we're told water flows out of the bottom of the tank through a tap at a rate proportional to the cube root of the volume. So we can actually write this mathematically. It is the water that's coming out, so it's the volume of water that is going to change, and it's at a rate, so it's over time. So you have a dV by dt. Okay. Now we've got proportional, so we can put our proportionality constant, and it's proportional to the cube root of the volume. However, because the water is leaking out of the tank or being removed from the tank, so it is a loss or a decrease, we can put a minus there. So actually we can rewrite this to get rid of the proportionality symbol to make it equal to minus some constant, we'll call this one c, of the cube root of the volume. So that's our first expression that we're going to need. Now, because the tank is cylindrical, you should be familiar with the volume of a cylinder, which is the area of the circle, because that's the upper or bottom surface of pi r squared times the height. Okay, so that is for our volume. Well, what we can say is we're going to need to get an expression for dH by dt. Now, we've got an expression here for dV by dt. So we've got our dt's, but we don't like this dV. So we need to get rid of the dV, and we do want a dH. So actually, we need to get an expression for either dH by dV, or from this, we can get an expression for dV by dH. So the differential of this with respect to h, the pi r squared is just a constant there, so the h disappears, leaving us with pi r squared. So we can actually substitute in at this point to say, therefore, dH by dt is equal to, we have dH by dV, which is 1 over this, so 1 over pi r squared, times dV by dt, which is minus c, the cube root of v. And we have an expression for our volume, so actually we can substitute in again. So we've got 1 over pi r squared times minus c, the cube root of pi r squared h. Now, this is going to be an expression for dH by dt, but actually in this problem we are given another value, which is for the diameter of the tank. The diameter is 20 metres. So we can use that to help us, because actually we can get a value for the radius of the tank, which is 10. And that's one of the reasons that we're able to differentiate this, because the radius is just a fixed value. So we can substitute in our value then for radius. So we've got 1 over 100 pi times minus c, the cube root of 100 pi h. which we can rewrite to get it into the form that we're looking for as minus c, the cube root of 100 pi over 100 pi times the cube root of h. And this c cube root of 100 pi over 100 pi is actually just another constant. So we can rewrite that as minus k times the cube root of h, which is what they are looking for. So therefore, dh by dt is equal to minus k times the cube root of h. So it's a little bit more complicated that. You end up with quite a nasty constant, but there's a reason that they're telling you to make it into this form, because it's going to make things a lot simpler in the next part of the problem. So now that we've got that, for part B we want to show that the general solution to this differential equation may be written as h is equal to p minus qt to the power of 3 over 2, where p and q are constants. So we're going to take this expression, dh by dt is equal to minus k. Well, we might as well write this as h to the 1 over 3, because we're going to use it in index notation. We need to do a little bit of rearrangement then to get the h's on one side, the t's on the other. So leave the k there, so minus k dt. This h to the 1/3, when it moves, it becomes h to the minus 1/3, because it's 1 over h to the 1 over 3, so it's h to the minus 3. Once you've separated your variables, we can integrate both sides. So h to the 1 over 3, when we integrate, you're going to get h raised to the power by 1 to the 2 over 3 divided by 2 over 3, which is the same as timesing by 3 over 2, is equal to minus k t plus some constant of integration c. So it's at this point we can do a slight rearrangement. The 3 over 2 becomes a multiplication of 2 over 3 on this side. So you've got 2 over 3c minus 2 over 3kt, and that's to the 2 over 3 there. To move the power, well, if it's a power of 2 over 3, when it moves, it flips. So really you have h is equal to 2 over 3c minus 2 over 3kt to the power of 3 over 2. And that is pretty much in the form that we want. So we can just rewrite this as h is equal to p minus qt to the 3 over 2, where p is equal to 2 over 3c and q is equal to 2 over 3k, where c and k are both constants. Just to clarify that, and if c is a constant, p must be a constant. If k is a constant, q must be a constant. And that's how we get it into that general solution. In the next video, we're going to look at using this general solution to find some particular solutions and to solve some equations.